Fine. Yeah. They have. Can get started. Good evening, everybody, and welcome to this evening's colloquium. I'm Prahlad Harsha, member of the School of Technology and Computer Science. Before I introduce the speaker and get started with today's event, I wanted to say a few words on behalf of the new a few words on the new colloquium series on behalf of the three organizers, Manoj Purvankara, Swarnava Mukhopadhyay, and Raghuvan Saxena. This is a new scientific lecture series designed to foster dialogue across scientists of all disciplines at the Mumbai campus of TIFR. The Colaba campus has a unique advantage that all the three schools, the School of Mathematics, the School of Natural Sciences, and the School of Technology and Computer Science share the same building, a proximity that makes it easier to nurture cross-disciplinary conversations. These talks will be aimed at a scientific audience from across the institute, and the series offers us a space, as a scientist, a space to engage with ideas both within and outside our own fields. The plan is to have about 6 to 8 such colloquia in this series spread across the year. These talks will typically happen in AG 66, which allows for a greater interactive feel, except in unusual circumstances like today, when all classrooms were booked for the just interviews. Since we are in a larger auditorium, I invite everyone to move forward so that the session feels a little more connected. And as talks in AG 66, we expect this to be an interactive session, so feel free to ask questions and stuff during the talk. We don't have to defer it to the end of the lecture. Okay, let's now come to the main. It's a real honor to invite as the inaugural speaker for this colloquium series, Professor Madhu Sudan, my PhD advisor at MIT, and now the Gordon McKay Professor at the School of Engineering and Applied Sciences at Harvard University. Madhu has done pioneering work on probabilistically checkable proofs and the design of list decoding algorithms for error correcting codes, which have profoundly shaped our understanding of reliable communication and computation. His current research explores property testing, fast sublinear time algorithms for massive data sets, something he'll be talking about in the talk, and communication amid uncertainty, a mathematical study of the role of context in communication. Madhu obtained his BTech from IIT Delhi in 1987 and his PhD from UC Berkeley in 1992, and has held positions at IBM Research, MIT, where he was the Fujitsu Chair Professor and the Associate Director of the Computer Science Laboratory, Microsoft Research, before joining Harvard in 2015. Madhu's many honors include the Gödel Prize, the Nevanlinna Prize, the Infosys Foundation Prize in Mathematical Sciences, and the IEEE Hamming Medal. He's a fellow of the ACM, IEEE, and AMS, and a member of both the American Academy of Arts and Sciences and the US National Academy of Sciences. Those who know Madhu and have interacted with him will agree, in addition to this, he's an extremely nice person. I consider myself very fortunate to have had him as an advisor. And over the years, he's not just been an advisor, but a colleague and a friend, and someone who remains my go-to person for just about everything. Over the last decade, he's been a frequent visitor to TIFR and is a friend of the department and the school, the institute. And so it's fitting that he's actually the inaugural speaker of the series. One more thing I want to say about Madhu. Madhu is a fantastic expositor. And two examples of this, yes, his courses on coding theory and algebra and computation, together with the lecture notes, have actually inspired us a generation of researchers in these areas. Another thing closer to heart is his exposition of the PCP theorem, co-authored with Jayakumar Radhakrishnan, remains one of the clearest and most approachable accounts for both mathematicians and computer science alike. He has been a true ambassador for our field. It's a great privilege to have him open this colloquium for us. Please join me in welcoming Professor Madhu Sudan.
Thanks, Prahlad. So Prahlad forgot to mention all the roles that I've played in his life, which is I graduated from being his advisor to being his student lately, and I've been learning a lot from my many, many visits to TIFR, thanks to Prahlad and many other collaborators over here, some of whom will be listed in the talk. So I'll apologize in advance. The slides were prepared kind of hastily and not under the best of circumstances. So I'll try my best to explain things that the slides are conveying in more broad language. But at any time, please do feel free to ask questions. If you raise a question and just shout it out and I can hear it, I'll repeat it to the rest of the audience. Don't worry about waiting for the mic, though there are microphones around. You can try to use them as well. All right, let's see if this works. Not yet. This talk, sorry, this was not a very deliberate or intentional choice, but this just happens to be from some of my slides from many years ago. Where does the big data problem come from? I just want to say that, look, it's been around for ages and ages and ages. So for example, here is this anecdote. I'm not a good historian. I'm definitely not an astronomer. Take this slide with a pinch of salt, but it should tell a good story. I mean, Tycho Brahe apparently spent 50-odd years in the late 16th century collecting data. And what did he want to do? He wanted to confirm this hypothesis that the Earth was the center of the universe and the sun revolved around it. He didn't quite manage to do that. So let's see. He did spend 10% of the Danish GNP, apparently, say some sources. And then Kepler came along, and he believed in Copernicus's picture that planets are moving in circular orbits, but with the sun at the center rather than the Earth at the center. And he also had actually an addendum saying that, look, okay, there's a precise ratio about how these the radii of these circles are growing, and these are somehow connected to the Platonic solids and so on. And again, he spent a lot of time, worked on it for 9 full years before he got some sort of a conclusion. And the conclusion said that, whoops, there's some lag over here that I'm trying to avoid. We'll see if I can find some good way to manage this. So he disproved the addendum. These ratios of these orbits were not quite that. He more or less confirmed Copernicus's conjecture with a slight modification. Circles had to be converted to ellipses, but at least, now it was confirmed that the sun was at the center of the universe, or at least the universe as we understood it then, and discovered the laws of planetary motion. So all of this is, taking 9 full years with the data in hand for Kepler. What is the big problem over here? Why is this take, in order to find, a collection of, fit a bunch of ellipses to some data, why does it take so long? And the challenge is some challenge that we continue to face to this date. And this is the kind of a challenge that I want to talk about. I'm not going to find a better way to have taken actual data and converted it into a theory, but at least I want to talk about the theory behind taking data and converting into a theory. So what's the question over here? There are many, many, many classes of incorrect hypotheses. You could have the sun at the center of the universe. You could have the Earth at the center. You could put Mars. You could put the moon. Whatever you want is a hypothesis. There are many, many classes of these incorrect hypotheses. You go around each one of them, ruling them out till you find the right set. And inside the set, you try to find what is the actual hypothesis. This is our process. But unfortunately, our process is even slower than that. When I have a class of hypotheses in mind, which may have n parameters describing a single hypothesis within the class, I spend time finding the best fitting hypothesis in this class. That takes at least n units of time. Just to even write down the hypothesis takes n units. And by the way, in modern machine learning technology, the size of the hypothesis often tends to be larger than the entire size of the data that you're reading in. Okay, so these are massive, massive systems, and you're trying to find all these parameters. And after you found all these parameters and you try to fit them to the data, and it doesn't really fit, so I have to toss out everything that I've done. So is there a better way to do this? Do you really need n units of time in order to say there is no hypothesis in this entire class that's actually going to fit the data at hand? So this is the question that we're going to ask today. And this question has been asked in my field, theoretical computer science, for about 40 years now, I think, give or take. And we've been coming up with definitions to support the concept and some results that support the concept. In particular, it's a kind of a coincidence. It's syntactically very similar. The biggest class of data analysis problems that we seem to have the best handle on is fitting polynomials to data. You have a multivariate polynomial, or you have a multivariate data space, and you want to understand, is there a polynomial that explains most of this? it seems this is one setup that we have very good understanding of, and I want to tell you a little bit about that. Okay. So mostly it's going to be an introduction to this problem called low degree testing problem. Is there a polynomial whose degree is, let's say, at most 50 in each variable, or 50 in all variables put together? That explains the data. Okay, that kind of a question is what we're going to be asking and understanding. And I'll try to tell you a little bit about what kinds of results do we know, what kinds of motivations do we have, and maybe just a little bit of a glimpse of the proof insights, though, if we don't get to that, I won't be most sad. All right, and I do want to mention one recent update. The questions that as you'll shortly see, the questions that we started talking about arose in the 90s, and lots of progress happened in the 90s, but it remained alive till very, very recently. And in fact, in work 2 years ago with Ramprasad, Mrinal, and Prahlad, who are all here, amazing co-authors. It's kind of very unfitting that I'm speaking about this result here, but on the other hand, I guess modesty prevents them from speaking about their results here. So maybe it's a good thing that's happening. So I'll tell you a little bit about this result. Not enough for you to know what the many ingredients are, but enough for you to maybe want to talk to them about further details. All right. So the broad context in this space called property testing, we're going to be looking at the data as if it's given by a function. Okay, it's a function which says given some input values, this is what the output value is. We're trying to say, is this function somehow nice? If it's a function of 10 variables and it's a polynomial of degree 3 in all the 10 variables together, that's probably nice. There may be other definitions of niceness. Pick any definition of niceness that you want, and then you can ask the question, is this data nice? And we would want to be able to look at this function, look at its values in a few places, and based on this, decide if it has that property. But we don't want to spend too much time doing it. And a proxy for time today is just how often do I ask you for the value of the function? Okay, if I ask for the value of the function at 5 places, that's great. If I ask them for the value of the function at 1 million places, that's probably not great. Okay, so that's the kind of a question that we are looking at. Okay. So the requirements that we would like to have are if this function has the property, and mathematically it can be captured by saying there's a set of functions which have the property, and if this function belongs to that set, let's say you must say yes. On the other hand, if we don't necessarily worry about functions that are small changes to functions in the family. If you have a polynomial that you've written its values down everywhere, and then you made a mistake somewhere and have a couple of outliers, we don't worry about it too much. But if you're close enough to a function that has this property, then we are happy to accept. That's the measure that we are going to be looking at. I'll formalize this a little bit more later. And then you can ask the question, are there functions that you can actually, are there properties that we can test for very accurately? Just to give you a sense of what is this question, what am I asking? Let's look at a very familiar old example, which is just polling a population for who's going to win the next election. Okay, so you have the function here takes names of people in the population and tells us which way they're going to vote, A or B. And we would like to know if a majority of the population is voting in favor of somebody. So let's say P sub alpha for some alpha, any parameter alpha that you choose is all functions that correspond to a alpha fraction of the population voting for one of the two parties. Okay. And we want to know if this can, if P sub alpha holds for the actual votes, opinions of the current population or not. Well, one way to do this would be to ask every member of the population which way they are voting. That's conducting an election in principle. But we all know that there is a good proxy for it, which is you just poll a bunch of random people and ask them what is their which way they're going to vote. This polling obviously has a little bit of a gap in the quality. If 50% of the population wants to vote for a particular party and you want to accept all of those rejections, saying all of these are definitely, yeah, this is a majority of X, then you can't quite say, I'll also reject anything that has 1% short of 50% votes. Polling has an inherent deficit. You have to sort of set a threshold far enough away. Maybe you set a threshold which is 1% away. Typical things that we run in normal polls is like a 3% margin of error. And if that's the case, then for a 3% margin of error, you roughly have to ask 1,000 people what they're thinking. And that gives you a sort of a qualitative result. So this is a setting where you set the threshold. How far from the truth do you want to get? And that tells you how many people you have to poll. It doesn't matter whether the population of the nation is 1 million, 1 billion, 1 trillion. It's the same 1,000 people for 3% error. Okay? This is the first example of a property that can be tested. This is an example of the kind of things that we are looking for. But this is work from, I don't know, I mean, we all think of this as sort of, folklore. Probably there was like a time 200 years ago where this would have been considered a revelation. But today, at least, we've known it forever. So what is new? What am I going to tell you today that's different? The different thing that I'm going to tell you today, by the way, there are many other examples that come from classical statistics. They all have this feature that, the value, whether the function has the property or not, is kind of independent about how the domain is named. Whether I say your vote is X and their vote is something else, or I flip the two names, it doesn't really matter. The property still holds. Okay, if I give all of your names, change your names to your PAN card numbers, the function value remains the same. Every one-to-one map on the function space, on the domain space, preserves the property of the function. These are very, very elementary properties to test. We are going to go much more sophisticated in the next slide. Yes, question, please. The question was, is there some distributional assumptions which say that this theorem, which says, asking 1,000 people to get a 3% confidence, if that holds? No, there are no distributional assumptions. However, there's a sampling assumption. Sampling assumption is I can find a uniform member of the population and ask them what is their vote. Okay. Every person is sampling. No, we don't care about outliers. If there are one person who is like, there's not much of a notion of an outlier over here because you either vote for party A or party B. If there are real valued functions and so on, then we have to put qualifiers on the statement. Okay, great. Thanks for the question. All right. So going to the more sophisticated example, this was a work done in 1990, which pretty much launched the space of property testing. And you're given a function, and we want to test if it's a homomorphism. So homomorphism is a mathematical word. What does it mean for us? Just think of it as if it's a function of m variables, which think real numbers today. The results hold for slightly different settings, but don't worry about it. And the function we are asking is there like m coefficients a1 to am, says that the function value on some point x is just a1 x1 plus a2 x2 plus a3 x3 and so on. Okay. We want to know this. We want to understand this. We want to know if f has this property. And this is sort of taking us to the Brahe, Kepler, Copernicus kind of an era, right? That was a higher degree polynomial, but at the end we are asking this kind of question. Is there such a fit to the data? And what do we want to do? We do not want to ask m questions. M questions is the least that you would expect based on your counts of the degrees of variables of independence to learn A1 to AM. How could I find out which A1 to AM are fitting the data if I don't ask M questions? But I do not want to ask M questions. So what do? Here's the Blum, Luby, Rubinfeld test. Said just pick two uniform members of the group. And sorry, at this stage, I have to sort of pretend that the real numbers sit in a finite set. It's going to be a little bit of an assumption, but yes, please. sorry, uniform. So this is where I have to assume that there's a finite set of values. So I'm going to assume that G, the function f maps a finite set G to a finite set H. And when I say uniform, I just want pick one of these elements exactly independent, uniformly and independent. Any one of these things has equal chance of being picked. Okay? So this, the result that I'm describing doesn't work over infinite spaces like real numbers, but it works over modular spaces like, you can even imagine doing this on a circle and so on. And in mathematics, in this space where I'm working with these objects, we work over what's called finite fields. And they pretty much behave like real numbers, except they're finite sets. So there's much value to this kind of a theorem. Perfect. So the question was, should I think of the group G as a finite dimensional vector space over a group of size 2? That would be a perfect example. H could be the group of size 2. We will even talk about that specific example in a moment. But yes, think of G as vectors of length n, but each coordinate of which is a bit, 0 or a 1. And when you add two of these numbers, 1 plus 1 becomes 0, but otherwise it looks like integer addition. Okay. So this is a perfect example of a setting where you can apply this theorem. And the test is very simple. Pick two elements, x and y, uniformly. Ask if f of x plus f of y equals f of x plus y. This should hold if the function looked like that summation ai xi. But the question is, okay, if this holds at these 3 points, what inference can you draw about the whole space? Think M is 100. The space of the group G, because it's 100 dimensional vectors, each one taking one of two values, is 2 to the 100. I'm looking at a function which is defined on 2 to the 100 input values. I'm looking at it in 3 places. And I've just checked some very local identity over here. Now I'm asking the question, can I say something about this entire 2 to the 100 valued function? Okay, function on 2 to the 100 values. And so this is the thing that I'm trying to emphasize. M parameters, but I'm not really allowed M units of time. I have no hope of guessing what A1 to AM are at this stage. But I'm asking the question, do they exist or not? Do I want to spend more time in exploring this data and trying to find what A1 to AM are? Or should I just scrap this hypothesis and move on to some other class? And the amazing theorem from Blum, Luby and Rubinfeld is that, of course, if the function was always satisfying this identity, we accept with probability 1, this would be a homomorphism. It does look like summation ai xi. But on the other hand, if the function actually has to be changed in, say, 10% of the places in order to get it to be a homomorphism, then you will also reject with probability at least, say, so with 1% probability. Okay. But we've only looked at the function at 3 places. So this is a super local test for a very, very, very global property. And this local to global phenomenon is the essence of this phenomenon that I want to talk to you about today, this local, this property testing space where we can do remarkable things looking at massive pieces of data by very, very local views. For me, local just means looking at the data in very few places, not necessarily geographically local places, but just very few places overall. 3 is very local for me. And 3 is a pretty good number for some of the examples later in the talk as well.
In general, it could fail so much more easily.
Exactly. So I think you are spot on. You are really, really speaking to the converted over here. You're saying, I don't believe this result because I've just looked at 3 values of the function. But notice, you could have picked a different set of 3 values. Well, maybe that would have also worked out okay. But if really 90% of the time, if you were picking 3 values, that would have worked. If, you can look a priori, you can look at this function that's written down and say, suppose 90% of the time I would have picked when I pick 3 values, things work. Is my function close? And the answer turns out to be yes. So proving that turns out to be quite non-trivial. I might talk about it in a slide or so. If I can get to this. Yes, actually, yeah. So here's, I'm flashing a slide over here of a proof. I'm not going to go through the proof with you, but I just do want to say a little bit about the style of reasoning which goes behind this. When this theorem came about, I was a graduate student doing my PhD. There was like a massive debate within the community as to, are you saying something completely trivial? Obviously, what you're saying is true. We all know that majority, can be tested for, and you're just testing some majority vote. Obviously, if your test passes with high probability, it should pass with high probability. And there was this proof which went very elaborately. So you give every member of the group R a vote saying, oh, what should this value of the nearby linear function be at a given point X? They all sit down and vote, and you analyze this voting function mathematically, and you try to prove that it's somehow coherent and consistent and comes up with a linear function at the end. If what you started was with the assumption that, most of the time, f of x plus f of y equals f of x plus y. For many choices, for 90% of all choices of the pair x, y, f of x plus f of y equals f of x plus y, then there's somebody nearby. So manufacturing this function turns out to be, very delicate. And in those days, we really didn't understand what was going on. There was a proof which was about 2 paragraphs long. There was absolutely no understanding of what was going on, except there was one line which was mysterious, proved everything you wanted, and, had to be, now you have to trust it, it's a proof, but no intuition whatsoever. But this was the kind of theorems that, we try to extend and understand and generalize later. And so this is something that I want to talk about more in the future. There's, by the way, other proof techniques that were invented to solve this particular problem, in particular in this case that Mahan was asking about, when the group is actually a vector space over a finite field and the domain is the field itself, then we can actually use extend the notion of Fourier analysis to the space, and leads to beautiful proofs over here. Ended up being an exceptionally rich area to start many, which launched many other directions within the field of computer science and mathematics. There's a very subtle change that I want to highlight again, which also relates to your question over there, that, when you use the vanilla version of this question, what you actually test for is f usually satisfies a certain property. F of x plus f of y equals f of x plus y. In the majority voting polling thing, also you tested for a property, which is if I usually ask a person, are they going to say they will vote red? In the case of majority, it was almost an obvious consequence that, yes, if they say they're usually going to be voting for red, then there is a function that I can obtain by changing my function slightly, which will actually have a majority of the portion people voting red. I only have to change a few values to make it an actual majority. In the case of linear functions, it's not clear that I can change a few values and now make it satisfy this equality everywhere. This change is what made the statement so hard to prove, and this is what we've been fighting against ever since. There's local ways of looking, global properties have local effects, but just observing a local effect does not imply the global property. This has to be proved, works in some cases, and when it works, we should sort of appreciate and relish. All right, so a little bit of history of this work. Mostly, I don't want to run through the whole thing. Really, we ran into a few properties. Yes, sorry, question. Yes, so today the distance measure that we're going to look at is how often do I have to change the function value? The domain of the functions will always be finite sized. And I will just ask the question, what % of values do I have to change? Great question. What is close? That's close. So roughly, I want to say the first 2 bullets over here talk about works that were done that were actually property testing results before we even invented the phrase, before we even realized there is a class of questions that we are looking at over here. Very soon after, we realized, oh, this has to be, there is a broad class of questions and we should be applying it in many, many broad contexts. And that happened in the mid-90s. And then it just launched a whole sequence of things. There have been graphical properties, statistical properties, matrix properties, properties of Boolean functions, et cetera, all kinds of things have been looked at. And but today's talk, I'm going to talk mostly about algebraic properties. The function look linear, degree 2, degree 10, degree d, etc. That's the kind of results that I want to talk about. All right, so low degree testing. So I'm given a function. Once again, I get to query its values at various places. It's always a multivariate function. And now the domain is going to be a vector space. Each variable takes values in a finite field. Numbers modulo some prime, for example, would be a pretty good example. Why study this question? When we, this has been one of the nicest experiences for us in this field as computer scientists. We ask these questions purely out of mathematical curiosity. There was something that was testing the limits of our understanding. We cannot understand it, so we need to. And I must say that this style has persisted throughout, including this latest work that I mentioned with my colleagues here at TIFR, that we asked the question saying, look, this is a natural question, it ought to be answered. And once we answered this question, somebody found applications, and it has happened all the time. Many applications that have been found since then. I will talk about one of these aspects now. It's called PCPs, or probabilistically checkable proofs. If people haven't heard about this concept, it's a separate takeaway from this talk. You can listen to this definition, hear what it's saying, and then think about it. Okay, so here's two proofs. One of them ends up proving, I don't know what the steps are, but the conclusion is 2 = 1. The other is pi = 3. These are just proofs from the web, okay? And these are proofs that are announced as being incorrect, but these are considered fun proofs, okay? Why are these fun? You go through these proofs and every line looks okay, except at some point, either in the line or between the lines, there's some assumption that has not been stated, and that assumption is not true, or that assumption makes the step of reasoning invalid. And so the inherent belief in proofs has always been, if I give you a million line proof, then you have to go through the million lines one step at a time till you find one step of reasoning which may be wrong. And if you do, then the proof is no longer valid. You can't say anything about the theorem being incorrect because the proof is wrong, but you can say the proof is not valid. Or you look at the whole thing and everything looks good, and now you know that the theorem is valid. Is it really necessary to look at the whole proof? This is the exact analogy of the property testing question. I have some massive data. In this case, the data is the proof of some theorem. And I want to know if it has a property. The property is this a valid proof of the theorem? And the miraculous thing that happens here is the answer is not under the following circumstances. There is a nice proof, but something a lot nicer. Let me tell you about it. But first, let me give you some definitions. So do the proofs have to be read in their entirety? That's the motivating question. If definition was then proposed in the 90s, saying this should be called a PCP, for probabilistically checkable proof. It should be a format in which you should be able to write proofs. So format, what do I mean by a format? Writing a proof in English is a format. Writing a proof in mathematical notation according to Zermelo-Frankel axioms is a format. Any way you can specify which allows you to verify the proof is a format. You should specify a format for writing proofs such that the format is verifiable by few queries. It sounds like an inherent contradiction given the examples from the previous page, but that was proof in a given current day format. We don't have to follow the given current day format. And when you do not, you get amazing objects like this PCP theorem that I was involved with in 1992, along with bunch of other folks in the community, which says that you can actually take any proof format and convert it to a probabilistically checkable one. The transformation will be quite non-standard. It'll be something that you're not used to thinking about, but it's a valid format. It's a, every valid statement that you want to prove has a proof in the new format. The new one will be slightly longer because it's now probabilistically checkable. So some redundancy is there and some, so it necessitates some growth in size. But on the other hand, you only need to look at this new proof in 3 bits. F of x plus f of y equals f of x plus y. Essentially the same 3 bits and the same same check more or less does it. And this kind of a test will convince you that the proof is correct or not. Now, how you choose the location x and y and this third location called x plus y is very, very carefully done. But there are going to be only 3 of these bits. And it's careful but very efficiently done. So everything is exceptionally fast over here. And this will tell us if the theorem is not correct, you can write anything you want, however deviously you want. I will not accept it with probability more than half. On the other hand, if the theorem is true, you have a valid proof, you can convert it to this format at a slight expense in the length, and now this whole thing will be true. Great. Question was, can we improve the probability, the confidence in the proof? Can you bootstrap this thing? And indeed, the answer is absolutely. In fact, the most naive way of doing this would be, so the probabilities in the statement are a function of how the verifier chooses x and y. Okay. So the verifier will choose some x, some y, and then look at x plus y. And these 3 locations will tell them, oh, okay, if this had been wrong, I would have detected it with probability 1/2. They can repeat this using fresh randomness, x prime, y prime, x prime plus y prime. Now the error probability will drop by another factor of 2. Every time you have a fresh 50% chance of catching this thing. There's a beautiful theory of work in this area which says, how can I recycle the queries? So do I really have to go to x and y and x plus y and then an x and a y, x prime and a y prime and an x prime for y prime? Or can I just reuse the same x? And maybe I can reuse the same y, and then maybe I can do more things. And in fact, actually, you can do a lot more and profit from it. At the end, for every 50% reduction in the error probability that you want, you read 1 more bit. And that's the limiting behavior. So it's really a remarkable thing. Every bit that you're reading, I could have written random things and you would have accepted it with the same-ish probability. So it's more or less like it's a miracle, but it's true. One more thing I want to mention is all these works that prove the PCP theorem rely on the linearity test or some local variant of it. And many variations also use the low degree test. In fact, the most efficient constructions that we know use the low degree test. So these are central ingredients, but they make questions as, standalone questions. I give you a multivariate function. Is it a low degree polynomial or not? Let me just take a look at the time, see how I'm doing. I have about 20 minutes or less.
Yeah, there's the following statement. If for a typical x and a typical y, then with high degree of one.
Great. So, yeah, great. No, that's exactly the right kind of a question. I think that that's appropriate for this audience. The question was, is it really the case that for a single x and a single y, if f of x plus f of y equals f of x plus y, or this proof says something is consistent, that gives me a lot of confidence? No, it's the statement, the underlying reasoning. So just like I cannot say, look, I found 10 people who are voting red today, and based on that, think that 90% of the population is going to vote red. These 10 people that I chose could be from the Republican convention and hence are going to vote red. Okay, so I have to have some confidence that this is happening for a uniformly chosen X. So, and that's in that sense, yes, the statement that I'm seeing should be an honest representation of the fraction of the population which satisfies this property. But the property that I'm looking for is just that there is, when I pick an X and a Y and I look at the X plus Y, these three values add up. Now, this X is involved in many other such triples, and that Y is involved in many other such triples. Maybe 5% of X triples fail, 5% of Y triples fail, 5% of X plus Y triples fail. How do I change everything, only 5% of all values, and get somebody that is satisfying this test everywhere? And we're saying you cannot be that only 5% of X and 5% of Y and 5% of X plus Y fail. Really, you must have 5% of X's which are failing and everything else is kind of happy. Question.
But typical was mentioned here for X plus Y, and you mentioned honest representation. And for my earlier question also, you had that it's a representative individual from the sample. But my point is, in reality, you will never know this for any real physical problem.
So
you can define mathematical systems with some degrees of freedom where you can, say this and then you can Monte Carlo it and do your proofs and show your probabilistic proofs are valid. But real data comes from real things that have underlying variables we don't know.
Right. So you can never hope that your sample comes from a uniform distribution. However, if you really have query access to this function, if you really have the ability to say, I want to study planetary motion, and I will ask the questions, where is the planet on a given day of time? And you get to choose the time, and you can choose your time by picking a random number from your computer using other objects. And then you ask the questions, then these things will work. But indeed, I mean, if I have to pick a random member of the population of India and ask them who they're going to vote for, how do I find this person? Sampling problems are definitely realistic problems for real life data, and a lot of study of data analysis is worried about the bias in sampling. I get data more easily from some samples than others, and that's absolutely, I agree, it's a valid point. But mathematically, if you don't have a theory which says even if you have access to the uniform random data, things will work, then trying to work on the sample axis is not going to help.
Yeah, I meant to say, even the planet example you use, you're using reduced representations of planets, and then you can do a bunch of precision analysis and find out things will diverge eventually. So
possibly, I mean, I must say, yeah.
We don't know how to solve anything more than even the three-body problem in Newtonian mechanics. You cannot solve to infinite precision. So after a while, it will diverge. And if you're thinking of time across long periods, then your domain is not closed or finite in the sense that you're or limited in the sense you're thinking.
So I think you have some questions that you are, I mean, you probably know more about it than I do. So let's take this offline and talk about it offline. Great. All right. So let's see, what is it that I wanted to say about these things? So maybe, so main considerations have been so one of the primary considerations in trying to understand when you have multivariate function, is this a degree D polynomial, is how often do I have to query this function value? And it was actually a miraculous result early in the literature where we realized that the number of places where you have to query the function value is a fixed function of the degree. It does not depend on the number of variables at all. Much later, we have realized that actually it's not even a fixed function of the degree. It is really the degree up to a constant factor. Okay. And the constant factor really depends on your level of confidence that you care about. Thank you. And even more recently, we've been starting to ask the question, okay, look, I want to look at this function, which is a massive global function, m-variate, many, each variable taking many values. And I'm looking at some very narrow projection of this function to a very small slice of places. And I'm asking, when I'm looking at it over here, does it look like a degree D polynomial on the whole space? There's some degree D polynomial in the whole space that it looks like. actually, this is, it's a solvable problem. It's actually something we can do something about. And B, if you measure even a tiny amount of correlation, we want to say, oh, actually, the whole thing was correlated. And this is where the work that I've been doing at TIFR has been, like, with collaborators here, has been very strong. Okay, so this is roughly the broad space of the questions that I want to tell you about. Now, I had a few slides on, how do these PCPs work look like? So I'll skip this thing. Okay, maybe just a little bit of, yes, sorry, yes, Mahan, go ahead.
Model, are you choosing a subspace of much smaller dimension judiciously and randomly?
Good. So the question was, how do you, get from multivariate function to some small dimensional question? And indeed, what we are going to do is we're going to pick a subspace. And you can think in real space also, but especially in the finite field vector spaces, that's exactly what we do. At the end, actually, so up until recently, we were all aware that when I looked at a multivariate function and projected it onto a two-dimensional surface, I get very good correlation behavior. If I notice some correlation here, I have global correlation. Our major improvement in the last couple of years has been, even if you look at a one-dimensional projection and you see something, a one-dimensional projection is a line. I'm just going to draw a line through this multidimensional space. Look at my function value here. If it's a polynomial of degree d in the whole space, it's a polynomial of degree d in this one-dimensional space. This one-dimensional degree d polynomial, I'm just going to see, is this one-dimensional function? I'm going to ask, is this really correlating well with some degree d polynomial? If it does, then I want to say the whole thing had correlation, and we can prove that. Great. So that's morally the result that we wanted to talk about, but really, this is a very geometric picture of the world. We are saying, oh, there's multidimensional space you're living in. There is a line that you're drawing, and then this line reveals some interesting behavior. In fact, to understand what happens on a line, we have to actually lift to two-dimensional surfaces and say, look, once you prove the theorem for two-dimensional polynomials, you're in great shape. And then, go from two-dimensional to m-dimensional, etc. The remarkable thing that happened in these proofs, and I'll try to was the original proof that we had was some, notice some linear equation was satisfied by one-variate polynomials, proved everything. Absolutely, had a bunch of equations out there. We threw it at this thing. It worked so great. We had no geometry. We had no intuition, just some equations that were working out. In fact, we really did not have the ability to reason about high-dimensional things because this was a univariate function. We were actually not even testing multivariate things. And some kind soul pointed to us that we could just put an m in the exponent of this thing there. The entire paper just translated to multivariate functions. Okay, that's really the truth. So it was just a remarkable coincidence that we discovered a very, very powerful high-dimensional theorem by just looking at this, one-dimensional object. Once we've had this thing, we said, okay, look, maybe we should look for some geometry and some intuition. Over time, we've been discovering more and more of it, and that has been able to tell us that really that there are you have very good global local to global properties. So, all right. So, I'm like, how am I doing on time? Maybe in the interest of time, I'll just sort of skip ahead to the ends of the things. Maybe a word or two, just a metaphoric thing. How did we go from polynomials and testing functions of polynomials to saying, I can prove anything to you where you can look at only a constant number of bits, 3 bits, and verify it. This comes through this, this algebraic view of computational complexity, which really says that, look, when we view data as a collection of bits, it's like looking at data as a piece of sand. It has all the rigidity and structure that you see over here. But what you can do is look at this data as coefficients of a polynomial. Okay, if I have 1,000 bytes of data, it's a polynomial of degree 1,000, whatever bytes mean. Okay, so that many things, 8,000, degree 8,000. Fine, it's a polynomial of degree something. Evaluate it in even more places. And now the data flips from being some, amorphous, this object that has no shape to something which is very rigid and very, very concrete. And now it's suddenly low degree testing also allows us to test integrity of this data. It says, look, I have this object that is supposed to be rigid. Is it really rigid? Low degree testing does exactly that. And once you have this low degree test, you can just somehow, use the following analogy. Analyzing a proof is trying to understand a few pieces that glue together. That's like inspecting a building, which is a few walls that are slapped on together. If you wanted to investigate the integrity of a building, you'd look at every atom in the building and say, oh, look, is this correct? Is this correct? Is this in the right place? It's going to take you forever. On the other hand, once you have these low degree tests, it sort of reduces to saying, are these few walls structurally placed right in the right way next to each other? And this analogy works all the way down to equations. Really, I mean, I can sort of, if I scroll through these things, I can sort of see 2 pages of proofs of equations, which really render all the things that we've been saying into, a formal mathematical proof. I won't run the proof by you, both out of interest of time and the fact that this is a new language for you. But the claim is there is actually, this analogy really works down to the core. And so we can really make proofs as robust and verification of proofs as robust as we think verification of large n particle systems is. So, right, so skipping all the proofs, skipping the, whoops, sorry. Just wanted to say that, yeah, so the final statement over here, the work with my collaborators here and so on, we really say that, look, if you look at the one-dimensional projections of functions on random lines and ask what's the expected distance from degree D polynomials, that distance is a very close proxy to the global distance of this function from degree D polynomials. And this is the kind of a theorem that makes, it's a easy to express theorem in general mathematical language, easy to appreciate, and extremely fun to prove with lots and lots of interesting elements. The next few slides were supposed to be about proof ingredients, what all went in there. I will not talk about them. I will also not talk about some extensive, other questions. But the main thing that I want to say is that we developed a deep understanding of this local to global structure of polynomials. What do they look like in many, 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 many variables can be inferred by looking at it, by looking at very, very tiny projections of these functions. And we hope that, in future directions, there are, many, many more questions that still need exploration. Sorry, these questions are a little too technical for this audience. Okay, so I'll stop here. Thank you.
No, so my question was the following. You had defined closeness as saying that it would fit a polynomial at most points, excepting a few. But can you all work with closeness in the sense that it's close to a polynomial at all points?
Great. So the question was, can we fit? Can we work with the definition, which is it close to a function at all points? We almost always have to sacrifice because we are not looking at the value of the function everywhere. We almost always have to sacrifice some fraction of the points and say that, look, you may need to change the function completely arbitrary on a tiny fraction. On the rest, you might ask for the question, which is, can we now change the value of the function minimally at the remaining points in order to get close to it? This is a beautiful question. Unfortunately, the kinds of answers that we are seeing over here are qualitatively worse, what we know is that the answer is going to be at least this much worse if we don't have upper bounds on it. So usually we would say, look, looking at the function value at degree many places or polynomial in the degree many places should be sufficient. In the kinds of questions that you're asking, we're forced to ask at least exponential in the degree many places. But even there, I don't think we have upper bounds, and these are very nice questions. Incidentally, there are some works that I'm not completely understanding of, called works on super resolution, which actually do tackle some of these questions, but they're very specific to the complex plane. And there are some very nice positive answers when the functions are defined on the complex circle.
Hi, that's a very nice talk. I'm completely out of this field. What I want to understand is, suppose I have a function which is maybe linear at a more close regime, some certain regime. So I want to understand how low is the low degree. Yes. So, or how would I quantify that how low I can use a value? Like you said, 3. So what sets that value to not 2 or 4, given the complication of the function? Even if it is suppose not, it is only piecewise linear in some regime, and I'm testing it. Am I clear what I'm trying to ask you?
The question makes sense. The answer, unfortunately, is not simple in the sense each property, we have to look at it, we have to stare at it, and then try to understand the structural aspects of it. Aspects like piecewise linearity, or can my function be explained by a few lines, even that version of the question. So there are a few lines, and can you explain your function by that? These kinds of questions, I mean, if I think of it as, can you explain it with a few lines? The answer can be yes, and I can test for that. How much will I query? Maybe dependent on the number of lines. Roughly, once I know if it's explained by a few lines, it's also explained by a polynomial, which is the product of these lines. That already gets us close to the low degree testing regime. And now you would ask the question, what's the degree of the polynomial, which is roughly the number of lines? And that will play a role in this thing. So you say, yes, the answers can be yes. But if you really cared about the function being piecewise linear, not just a slapped together union of lines, then the problem might suddenly become very different in complexity.
Probably, and you skipped over this. There was some place where you mentioned expanders with small number of variables, something like that. And this exponential efficiency seems to have echoes in the expander world. So if you could just spend a couple of minutes on that, it would be great.
Sure. Let me see if I can scroll back to that. So perhaps this kind of a slide or something before this.
This was actually, I think,
Yeah.
some
So
application.
a kind of object that we often explore in this thing is the graph of incidences. So I put all the points on one side of the, in a space on one side. On the other side, I list all the lines. And by the way, points and lines are all finite in this finite space. And then draw an incidence, a line if the point sits in the line. Then we start exploring properties of this graph. And the more properties you can extract from this graph, the more you can use in the low degree testing and analysis. The first class of results more or less looked at this graph and said, I know almost everything about it and really don't need to say much more than that. Later things needed to look at layers of this graph. I draw points and then lines and then planes and then m-dimensional surfaces and look at all the containments here and there and say that even local pieces of this are going to be very expanding. And that theory called high dimensional expansion, so something that Prahlad and Ramprasad here all worked on extensively. These theories have been extremely useful, some in retrospect and some future looking and predicted new phenomena. Thank you all.